to the substrate, then deposit it into the solution of inorganic materials, for instance, negatively charged clay sheets. Rinse off. Again, it leaves very strongly adsorbed film of carbon nanotubes, of clay sheets. And after that, you can repeat this cycle again and again, and so build up the material layer by layer, combining organic materials and inorganic materials. So this technique is very versatile. It allows one to use many kinds of polymers, many kinds of inorganic materials. It also has quite a lot of advantages in respect to mechanics of the resulting composites. We have here a high degree of control over the structure. We also can produce the materials with the greatest possible volume density of the interfaces, just because of the manufacturing technique that we have. We also can combine, say, electrically conductive materials with high-strength materials and the others. This would lead us to multifunctional materials. Last but not the least, this process is very environmentally benign. It uses very inexpensive clay components, which are dirt cheap, and also it uses only water dispersions, which also create a very minimal pollution. It also has some disadvantages because it's deposition layer by layer of 1 nanometer scale, a layer at a time. It's not very fast, and that needs to be addressed, and I will talk about it later on in the presentation. But now let's have a look what kind of structures and what kind of mechanical properties we can obtain when we combine fairly simple polymeric materials and clay sheets. Indeed, LBL composites from clay replicate the structure of the nacre and motherboard very well. We see here scanning electron microscopies of nacre and LBL composites of clays. They're very much identical, except that the interfaces and the size of these inorganic sheets in LBL structures are at nanometer scale, which is very beneficial for the mechanical properties. I also want to draw your attention to the fact that these films, which we separated from the glass slide, are very transparent. And this would lend itself to the potential production of high-strength transparent armor materials. It's also quite important to point out that the loading of clay here very high. As you remember, it benefits the mechanical properties, but also we need to be mindful when we develop the ballast protective armor, for instance, about flammability, and high content of inorganic materials drastically reduces the flammability. Mechanical properties here, as you can see, are quite exceptional. The tensile strength is 400 megapascals, Young's modulus is 100 gigapascals, so by any type of the measure, this is the strongest composite from clay that had ever been created. We can also compare it to the more traditional materials such as Kevlar and steel and copper, and for each of them we see the favorable comparison. One point which I want to make in respect to the steel, maybe this is not the highest grade of steel, but this is the most common grade of steel. And the density of the LBL composites from clay is much smaller than the steel, while the mechanical properties are very competitive. In fact, the Young's modulus and the the tensile strength are greater than that in that kind of steel. When we're thinking about the armor, we always need to think about the density and the potential weight of the armor. And so one can also compare these mechanical properties to the traditional components of the transparent armor, for instance, lexane and Scotch guard and nylon and glass, and some of them are used as relatively thick sheets of transparent armor. Some of them are used in between material for as gaskets, if you want, between the lexane and glass. And in many aspects, LBL composites exceeding the mechanical properties of all of them that that are currently used in the transparent armor. You remember that LBL technology is quite universal. Let's have a look what we can get with other type of the inorganic nanoscale materials, for instance, carbon nanotubes. We can repeat this process for them, and the idea here is again quite simple. We use initially the glass substrate, put it into the solution of positively charged polyelectrolyte, rinse it off, put it then into the solution of negatively charged carbon nanotube, rinse it off, repeat this cycle, build up layer by layer carbon nanotube polymer, fill up the structure, and in the end we have very uniform carbon nanotube composite materials with high content of the high strength inorganic structures. And indeed, this results in truly amazing mechanical parameters and mechanical properties. In fact, just like for clay, here this kind of composites, they beat the records of other bulk carbon nanotube composites. It's interesting to compare them with high strength materials such as maybe silk or Kevlar or some others. And I'd like to draw your attention to one particular parameter, which is the toughness. This is the most probably important mechanical property when we're speaking about armor, because it directly relates to the amount of energy dissipated in the material, and the toughness of this kind of composite structures is 3 times greater than the toughness of Kevlar. The tensile strength and Young's modulus are not as high, but here I would like to point out also that many of these parameters had been obtained for the very slow deformation of the corresponding materials. And the actual performance of the armor for the ballistic protection and blast protection should be determined for high rate deformation. This is kind of important aspect which currently the science of ballistic protection needs still to embrace, and to understand better how the performance at the slow rates depends and correlates with the performance at high rate deformations. And so with this in mind, we also need to point out that we do need to have here the testing of these materials at high rate, which we're getting ready to do at the University of Michigan. The weight and the mechanical properties need to be looked at for ballistic protection simultaneously. And that can be done by using the so-called Ashby plots. They typically combine 2 types of parameters, and the Ashby plot here represents the Young's modulus and the density of the materials. And here we have all the materials available currently, the blank parts of the Ashby plots, they represent these combinations of density and Young's modulus, which are very hard to obtain. In fact, there are no current materials which can fill these areas. And the part with low density, high Young's modulus, for instance, are particularly important for the armor type of the materials. And let's have a look where we have the performance in that respect of LBL films, and both for clay LBL films and carbon nanotubes films, we see that these combinations go straight in the middle of the blank part of the Ashby plot, which again indicates that these are quite unique materials. And so as long as we have that kind of composites, and as you remember, the clay composites are also transparent, we were interested to see how they actually behave for transparent armor, for instance. And so initially in the laboratory setting, we created a prototype of the transparent armor utilizing this kind of composites. We took thin glass sheets with a thickness about 1.1 millimeter and deposited on each side very thin films of LBL clay composites. The thickness of the film was about 10 micron. This is 100 times smaller than the thickness of the glass. And let's see how different or how much difference this kind of sheet would make, this kind of layer will make on the ballistic performance of the transparent armor prototype that we will have here. We took 4 of these sheets, consolidated them together, and performed the laboratory projectile testing here. Indeed, the material performed here quite well, and as expected, we saw quite a lot of formation of the fine cracks, which indicate that the energy of this projectile impact is absorbed in the bulk of the clay composite as well as in the glass sheets. Also quite interesting to point out that these kind of layered consolidated structures, they acquire quite a bit of elastic properties. And so on the back plate, you see that the bullet resulted in indentation, but not in the hole, and not in the formation of the big shards, big fractures, as it is very traditional for the glass. And so indeed, this kind of